Okay, so we will continue our talks about the ALF. And today, Francesco Parisen Toldin, who is in Aachen now, will tell us about the observables in the ALF code. And so the stage is yours. And so if you have questions, you can just ask him within, but then I have to show you the catch box. I'll do my best to hit right. And so you can start. Thank you.
Okay, thank you. So I will cover then the observable as they are structured in the ALF package. This is a brief outline of the talk. I will first present you the way the observable are stored inside the program, so the types and how they are defined. Then we'll move to show you some of the most important predefined observable. We have a big set of observables which are already predefined and have a common structure. And then, of course, one often is a case that one wants to define its own observable, and then we'll cover this in the last point. So let's move to the first point, the observable type in the ALF package. So I will recall that you have probably seen in the previous lectures that generically we compute the expectation value of an observable by averaging over the Monte Carlo measurements, and this average, in case the model with this representation has a sign problem, is already automatically reweighted over the possible sign and phase that the QMC configuration might have. As you can see already from this expression, we have two kinds of average. One is the average over the Monte Carlo steps, and the other one is the expectation value at the given configuration of the Haber-Stratonowicz field, which I will show later, can be computed on the basis of the Green's functions. We have basically three types of observables. One are the so-called scalar observables. These are observables like the magnetization, the energy, so simple numbers. During the Monte Carlo sweeps, the program does an update from sweeping the time slices to which the imaginary time propagation is sliced from 0 to L trot. You can control in the parameters file when in these slices the average, the Monte Carlo measures are done. Usually you would like to have the scalar observable to be average at each slice in the imaginary time, so that you have an improved average value, but it is also possible to decide the starting point and the end point of the measurements of scalar observable by indicating this parameter LOPS start and LOPS end in the parameters file. These scalar observables, they are stored in a Fortran type, which we define inside the ALF. It's called observec. This is a type which holds the various information about the observables, in particular the number of measurements that has been done. That is useful for computing eventually the average. The average sign, the one that you use for reweighting in case the model has a sign problem. And an obsvec, which is a vector of complex number that contains the average, or better, the accumulated measurements you have accumulated during the sampling. And then there are a few of other fields which contains, for example, the output file where it is stored, or some description, and so on, and some analysis mode, which depends on how you would like to compute the analysis of this observable. In general, for a given observable, a scalar observable, we have two outputs. The name of the observable underscore scal contains the actual measurements. For example, the energy, it's nr underscore scal. And then there is another file with an extra underscore info, which contains some information on the observable. Next to the scalar observable, another important class of observables are the equal time correlations. So these are correlations, the two-point function of some observable measured at the same imaginary time, and the two-point function displaced along the lattice. Now, in general, generically, we can say that we have an index, I minus j, which measures the distance at which this two-point function is computed. And in case the lattice has a unit cell that has more than one element, then we can, for every element of the unit cell, we could possibly define a local observable, and then the two-point function will be an n times n matrix, where n is the number of the sites in the unit cell. Now the alpha, given this construction of the two-point function, automatically compute the Fourier transform. So what you save and you see in the output file is already transformed according to the momenta of the underlying lattice. Here's, for example, an observable, a typical case of equal time observable are, for example, density or spin-spin correlations. Next to it, we also have the time-displaced correlation functions, which the structure is similar, only that now we also have an additional index, which is the time tau, at which this correlation is computed. Again, we have an automatic Fourier transform in space, so the quantity which is then saved on the disk will be generically an n times n matrix, depending on the momentum k and on the time slice tau. It should be noticed that often the time-displaced correlations are expensive, and for this reason, unless you really need it, you may want to disable the computation of it. And so there is a specific parameter in the parameters file, L tau, which, depending if it's set to 1 or to 0, computes or does not compute the time-displaced correlations. The equal time and the time-displaced correlations are stored again in the Fortran type called obserlat. Well, again, we have a series of fields which contains information on the observable, in particular the number of measurements that is used to take the average sign. Now we have also this obslat, which will be in general an array depending on several parameters. The first one is the distance in space, where the correlation is computed. The second is a time, or this is absent, of course, if we are talking about the equal time correlation, and then two indexes reflecting the unit cell index. For the two-point function, since generically you would like to have the connected part, so the one where you subtract the product of the expectation value, of course, you need also to store the expectation value of the observable itself, which then does not depend neither on time or space and only on the index of the unit cell. And again, we have a series of other information concerning the structure, the lattice structure, and the name of the observables. Now, I would like to point the attention that each observable can have its own lattice and unit cell. So this is particularly useful. It gives you an extra flexibility in defining the correlations, because it means that depending on the type of correlation, they may live in a different lattice. For example, imagine you want to compute a time-displaced correlation of a scalar observables, then you can embed this into a structure like this one, where the lattice is trivially has just one site, so just a single value of the scalar observable, but a possible time displacement. So this is why you have this extra flexibility of indicating or using a different lattice and unit cell for any observable. And again, we have a convention for the output file. The underscore ec means the equal time correlations, underscore tau, the time displaced correlations. And again, the info file contains some extra information on the correlations. Now, this is the general structure where this is stored. The ALF comes already with a library of predefined observables, the one which are probably most useful. Generically, all the observables are defined by subroutines which are named predefined underscore ops, and then the name of the observable. All these routines, they typically takes as parameter a series of data, which I indicate here. We try as much as possible to have a similar syntax, so that we have a similar consistent way to define the routines with predefined observables. In particular, the predefined observable receive as index the data concerning the lattice, so the lattice and unit cell. A list which basically is a map of from a lattice sites and the unit cell to a big super index of the entire lattice. And then the predefined observable can be computed generically using the Green's function. And then depending whether this is a time displaced or equal time correlations, the routines needs the equal time Green's function, GRGC, or the time displaced one, which we have here. And then again, there is a few other parameters which, depending on the observables, are used, like, for example, the value of the sign and the phase if the model has a sign problem, and the number of colors, of SUN colors of the model. So this is a parameter that says that we have n fermions which enjoy a full SUN symmetry, which remains also at the level of the Haber-Satonovich. So here I'm giving you a few of examples of the most important equal time correlation. For example, we have a routine computing the spin-spin correlation. These are called SUN correlation because they assume that you have n SUN fermions, so we have an invariance under SUN with n given here in these parameters. And then the two-point function corresponds to this observable here. So simply the spin written in terms of the generator of the SUN algebra, and then the connected two-point function. Okay. Typically you use this observable when you have just one flavor, but it is also possible to have it for more than one flavor. Then you should check also the documentation. Equally, you could have the case of computing the spin-spin correlations in a model where you don't have a full SU2 symmetry, but rather you have a U1 symmetry, either because the model is already only U1 symmetric, or because you have introduced a Haber-Satonovich decomposition which breaks explicitly the SU2 symmetry. In both cases, this is treated by having a different number of flavors, different flavors, and for example, a single SUN flavor. You see here in this example that for n SUN equal 1 and flavor equal 2, basically this spin-spin correlation outputs the ZZ component of the spin-spin and the XY component. This observable then, this routine returns then the ZZ component, the XY component, and the average sum. So in case this is also useful to have. We have also a library for time displaced correlations. They pretty much work the same. This is, for example, the spin correlation in space and in time. The only difference is that as a parameter, it requires the time displaced correlation Green's function, so the GT0, 0T, 00, and TT. But the syntax is otherwise very similar. And same also goes for example, for the spin correlation, where you have broken the SU2 symmetry to a U1 symmetry. These are only, of course, some of the observable. You can check the documentation. There are many others observable. Of course, next to the spin-spin, there is the Green's functions. There are the density correlation dimers, some more specific observable related to the Kondo lattice models, and so on. And there is a growing list of predefined observables. A particular set of observable, which is slightly different also in the syntax, and has been introduced from the version 2 of the ALF, concerns the entanglement entropies. So very quickly, how do you define the entanglement entropy? You imagine to have B the entire Hilbert space, and you define a subsystem A, and the reduced density matrix is obtained by taking the full density matrix of the system and tracing out the degrees of freedom of B. Then you get a reduced density matrix for the subsystem A. From there, one can define the so-called Rayleigh entropies by taking the trace of the power of rho A. And these Rayleigh entropies have a lot of properties that are also reviewed. So I'm not talking now. For example, they have an error law, there are corrections to it, which give a lot of useful information like the central charging, conformality theories, and so on. In the alpha from the version 2.0, you can also measure these Rayleigh entropies. Specifically, there is a module called entanglement mod. And it should be noticed that this works only when the MPI is enabled and you have at least 2 tasks. And this modules comes with a predefined observable that computes some observable obs such that its expectation value is the exponential of the second Rayleigh entropy. So we only compute in this module the second Rayleigh entropy. And as you can see from the definition, you need to somehow define what you call the subsystem A, for which you compute the Rayleigh entropies. And we have foreseen 3 possible cases. In the first case, that's the most general one. For every flavor and for every SUN fermions, for every SUN index, we provide a list of sites that belong to the subsystem A. So the bipartition is always in real space. And this comes, of course, together with an array telling you for each N flavor and SUN fermion how many sites you have. Okay? So in this case, then the syntax is just this one, but you don't put N SUN in the call. Then there is the case where you have the same sites for all colors, so all N SUN colors of the fermions. In which case you provide a list which has 1 less element. So this is the N SUN is the same for all the 3. Again, for each flavor, a list of sites and the number of sites that you have for each flavor. And here you provide with N SUN a list of color indexes for each given flavor. And then the case which is symmetric in color and in flavors, then you just provide a list of lattices and the number of sites and the number of color indexes of the subsystem A. Another closely related quantity, which the entanglement module is able to compute, is the mutual information. In this case, you define 2 subsystems A and B, and the mutual information is defined by taking the sum of the Rayleigh entropies in A and B minus the sum of the Rayleigh entropy of the union. So basically, you compute the 3 different Rayleigh entropies, and the calling of this subroutine of scal mutual inf is very similar. So again, you have to provide a list for A and a list for B using the same syntax as before. So with the 3 different cases. As I said, we have already a quite good list of commonly used observables for many models. Chances are, of course, that you would like to define your own observables. And this is, of course, possible upon a modification of the program. So the first things to know is that if you want to implement a new type of observables, you have to modify the Hamiltonian submodule in order to declare these observables, so allocate the space for it, and then be sure that this observable is actually sampled during the Monte Carlo. So this is if you look inside the program Hamiltonians, there are several modules depending on the Hamiltonian. And inside of these modules, there are 3 subroutines which we have to look. One is called the alloc obs. This is the subroutine which allocates the space for every observable. So if you have a new observables, you have to declare it here and allocate the space. You can look also inside the code to see how the various time displaced or space correlation or scalar observable are declared. Then there are 2 routines, the subroutine observe and the subroutine observe T, which contains the call to the routine that measure the actual time displaced or equal time observable. So if you have defined a new routine that computes your specific observable, then you have to remember to insert here or here the call to this observable. That's all you have to modify in the main program. And of course, you have to implement the actual observable by defining some routines. How do you do that? Well, the general procedure is that you write the observable you want to compute in terms of the fermionic creation and annihilation operators. And then you exploit the fact that after the Haber-Satonovich, the way really the auxiliary field is formulated, the system after a Haber-Satonovich decomposition is a free fermionic system. And being a free fermionic system, every possible observable can be reduced via the Wick's theorem to a combination of the Green's function. So, for example, this is an example of a 4 fermions observable, which using the Wick's theorem can be computed in terms of the combination of the Green's functions. These Green's functions are always available inside the Monte Carlo run. In particular, we have there are always defined inside the Monte Carlo run the GR and GRC, the equal time Green's function, and also the time displaced Green's function. It should be noticed that when the program is updating the slice tau, you just have the Green's function displaced from tau to 0, tau tau, or 0 0, but not for a generic different tau. Okay. And these are the typical parameters that you would like to pass to your own subroutine. And we advise you to follow the similar syntax like we had in our predefined observable, where you pass some lattice information, some list, and then the required Green's function. So we advise you to follow this convention. And then using this Green's function that you are supposed to pass to your subroutine, you are able then using the Wick's theorem to compute the various your own custom observables. As I said, we have already a good list of observables, but you are of course very welcome to join us on the GitLab by asking if there are some specific observables that you would like to have, or you can of course try to implement it and contact us or join us on the GitHub to open an issue and resolve your specific observable. With that, I'm done with the presentation, and I'm happy to take some questions.
Thank you. So are there first questions from the audience here or in the Zoom?
Yes, I would have a few questions. I got an answer, but I'm not sure how to interpret it in the chat. I mean, first you have shown the static structure factor, the Fourier transform of the correlation function. And there you had this SK with yes, that was it, with sub-indices alpha beta. And I was told that these alpha beta are orbital indices. I'm not sure what that means. I mean, if that I and J runs over unit cells only and not over the sublattice indices, then I guess that alpha beta are the sublattice indices, aren't they?
Yes, so alpha and beta can be thought, for example, as a sublattice of the system. So in this, for example, in this example, no, you have a honeycomb lattice. The unit cell has two sides, A and B. Then
Okay.
the spin-spin correlation will be a 2 by 2 matrix. No, the AA, AB, BA, BB correlation.
Yeah.
But it can be more general than that, because if you define a custom observable, for example, imagine that out of this honeycomb lattice, you want to, in each cell, just measure a single observable, say some combination of the AA, BB, whatever, okay?
Mm-hmm.
Then you can do this by defining a specific observable which has its own lattice structure, so its own unit cell and its own lattice structure. This is also possible. So that comes, it's stored inside, wait a second. It's stored inside the observed lat structure. So there is a lat unit and lat. So this can be, they can be different than the underlying lattice of the model in this sense.
Mm-hmm.
Or in simplest case, you can think that the lattice and the unit lattice of the observable are the same of the model. So in this case, then the alpha and beta are simply the orbital index of the unit cell.
Okay, thank you. And I would have one more question. You talked about S2N symmetry and that you can measure S2N symmetric structure factor with replacing the spin operators with the S2N generators of the Lie algebra. And my question is, if these are fermions, then in the SO2 case, you do half filling, and in that case, all the representations of the I mean, if you think about this as a multi-insulator and you get a Heisenberg model, then these are just the spin operators in the SON case or something like that. And depending on the fermionic picture which gives rise to that, you have different representations in the SO1 case. In the SO2, it's all the same because you always have half filling in the multi-insulator case. So you get just one representation in the Heisenberg model. But in the SO1 case, you can have n fermions per site, n flavors per site. I mean, if you have 4 flavors, you can have one site with 4 flavors, not just a singly occupied or half-filled case. And my question is, can you modify the filling of the sites so that you can get different representations of the Heisenberg model? Because typically...
Yeah. I think you are thinking about a subset of representation, the one that you imagine like a column in the Young tableau, and you have
exactly.
Right. Okay, so that you can do by formulating a model that has a specific filling, and in that for that class of representation, the generator of SUN in this representation are really written in this way: C dagger T C.
Yes.
Only for this class of representation. And so in this case, then this is already the formula you need. And if you have want to have a different representation, you simply have a different filling factor.
Okay, my question is, first, if I change the representation by changing the filling, the matrix TA changes, at least its size. And also, as far as I heard, most quantum Monte Carlo methods have a sign problem when you are away from half filling. My question is, can you do singly occupied sites, 1/n filling? That's the fundamental representation.
I think that to implement this representation, you have to...
That's one box in the Young tableau.
You have to, yes, I understand. You need, first of all, to fix, so for having a column, you need to fix the number, the occupation.
Yes.
That's if you go very far away from half filling, I think you incur in a serious sign problem. So it will be difficult to get something different than the half column.
So let me comment on this. Yeah. We tried this a long time ago. So you're correct. You can just fill. You can. For example, the SU4 fundamental representation, it's Kugelkomsky, has very nice physics. We get a sign problem, right?
Hell, that was what I was interested in.
Yeah, so that's already been tried, and you don't even get to the mod insulator. So I tried that some time ago, and it doesn't work. That's like, so the fundament, you really are stuck to particle hole symmetry, and the particle hole symmetry, at least for these systems we do in SUN, that forces you to work with the totally antisymmetric, self-adjoint. I don't know how many words you have to use to formulate that. That's how it goes.
Thank you.
Are there more questions? Maybe I have one.
Yeah.
So for what case values do you save the observables which are Fourier transformed usually? Do you just save basically at the high symmetry points, or do you go into some?
I mean, not sure I understood. The ALF does here Fourier transform and stores all the momenta. So
yeah, but for what momentum you will? I mean, in the files, there will be S of k, right?
Yes, no, they are saved one after the other. There's a format like then the K momentum and then the measurements.
Okay.
And there is another K momentum and the measurements.
Okay. More questions? Okay, and what if you have some correlation function where you basically want to measure the Green's function at some different arbitrary time steps? I don't know. So do you have to save the full Green's function at the beginning of a measurement, so that at the beginning of a sweep, so that you have the full matrix and basically n tau times n tau?
You want the equal time Green's function, but at different time steps?
No, I want basically d of tau tau prime, something like this.
I mean, in the alpha, you always measure 0 tau and tau 0 at the given tau, you mean. Now, maybe if you use the translational invariance, you transform your tau tau prime after average the Monte Carlo into a 0 tau minus tau prime. After averaging.
I want to basically measure, for example, for the current correlator, when I measure this, I would need to have tau at two different times, g of tau prime, right? Yeah, but it was just to ask for people. Yeah. Okay.
I have a question.
Very nice. Yes, go ahead.
So how do we get the errors for the observables? I'm not sure.
So there is an analysis program which implements the jackknife over and comes already with some scripts. Implements the jackknife over all these observables which are saved basically. And then it gives you for every k the value of the full n by n matrix of the correlation for examples with its error bar.
Okay. Okay. Thanks.
So to continue your question, so we have tau and tau prime basically, but what we don't have, there are a lot of physics beyond linear response, right? So if you do linear response, you have two times. If you do you know, I don't know how you call it, beyond linear response, then you need three times, right? And then we don't have that. We don't have access to these things, right? So I mean, we have equal time, we have time displaced, but basically two time differences, which we would need for nonlinear response, it's called, which is very interesting these days. We don't know how to do that for them. We would know how to do this, but it would cost a bit of time.
Could you do that to implement this by advancing some of the Green's functions?
Yeah, it's a painful bookkeeping, right?
Yeah, so I'm not even sure if you have stability issues.
Yeah, I'm not sure even. I don't even know myself if we would have an issue or not. I think it's it's an interesting. It is certainly because so I'm saying this because there are a lot of articles or people you go to more and more conferences and you see that people are measuring nonlinear responses, right? And they claim that in the nonlinear response they are, you know, defining signatures of fractionalization or things like that. I'm not sure I understand the details, but it's certainly one way in which the experimentalists are going. And it would be very interesting, I think, to sit down and see if we can do something there. But, you know, never had the time. Do you ever think about it, Jonas, or did you? Okay, so careful, box is coming.
I think we were discussing about this maybe with Emily at some point or with somebody else. I don't know, but I think this topic came up if we can measure correlation functions not between 2 points in time but 3 points in time, and I guess it should be possible, but one of the tricky parts, it's a little bit more involved in it's more expensive in the calculations overall. And for the time displaced correlation functions, if I'm not mistaken, we build a matrix where we have the 2 times that we then invert to stabilize the Green's function. I don't see a reason why this would not work if we have 3 copies. So I don't think there is a fundamental obstruction to getting there. It's just expensive.
Well, we're doing this for the ready entry. I had 3 times. You not have to-
Actually, no. Actually,
actually,
actually, that's 2 times. That is 2 times, but it's not 0 and top, but maybe theta and top. Yeah, and I have to update at each step. Yeah.
I do that. I mean, I also have, I mean, if it's between us, but I have this, it's also between 2 different times, but it's like L tau minus beta, which is also not in. So what I do is I always save the full Green's function matrix at the end of, while he goes through the time size in the next sweep, basically I can, or at the end of this, when he goes through the time sizes, I can measure the observable. And I guess you could do that then with also higher, I mean, I don't know, 3 time sizes and so on and so forth. If you save the whole matrix, right?
Yeah. I think we would have access to this, but we would have to find a good problem and try to see how easy it is to run.
Some other comments or questions or comments on that particular?
I would
Yeah.
have one more question. When you talk about the time displaced Green's function, there were cases when you wrote tau 0. I understand that's time displaced, but when you write tau, it's equal time, right? I mean, if C dagger tau, C tau, the expectation value, that's equal time, or isn't it?
Yes, it's equal time, but at this specific time slices.
So may it be different from the expectation value of C dagger 0, C0? I mean,
the G00 on average not, but on a specific Haber-Satonovich configuration, yes.
Okay.
You break the translational symmetry in time.
Okay, thank you.
Okay.
I have a suggestion instead of a question. So I wonder if it is possible to include the zero frequency observable. I know it is not super necessary because one can do the time integration from the unequal time observable, but it is just convenient to have that. For example, it becomes important for like observing the stripe, and it is also important for bookkeeping, because if one only need the zero frequency, then we don't need to save the whole unequal time observable.
So the zero frequency is produced in the analysis.
I see.
It's called tau J, something like that. And then but you have to be a bit careful with this. It produces the trace. I forgot. You have to be very careful if we have multi-orbitals, what exactly this produces. You have to read the documentation. That I would really encourage you to do that. And it's something which is post-process after measuring the time displaced. So you don't measure it directly. You measure first the time displaced, and then you have to store the time displaced, and then you have the zero frequency via integration. Maybe you could do it better. Okay, careful this time. I'm going to see if I'm going to. No, I'm not going.
Yeah, so I think all the default observables that we have at the moment, when there are time displays, they measure time display Green's functions and keep all the information, just like Bakir was saying. If this is getting too, well, not really compute expensive, but probably disk space expensive for you, there is a chance, like you can implement the time integration in the observt function, and then only store the zero frequency component. Or if you like, you can also go to a subset of Matsubara frequencies and store those. But by default, it's done in post-processing, but not at the Monte Carlo sampling time. So this would be an observable that one has to implement yourself.
You need to be sure that when it's the sweep is over to store it, and then
yes,
that's the thing. You have to check whether the tau is equal to L tau, and then you stop doing the integration and save the number.
Yes. Yes.
I see. Thank you.